In this section, we're going to start with the artificial kidney, which is not really artificial kidney, but dialysis. All right. All right. So imagine you've got your blood volume here, which is, um, well, you got your blood volume here, and you've got your dialysis fluid, and you're going to um, run your blood volume over a membrane in which the other side is your dialysis fluid. Well, if you make the volume of your dialysis fluid much larger than the volume of your blood, then you can set the concentration of solute you're after in the dialysis fluid, and the blood volume fluid will drift that way, right? And so we're talking about diffusion only. There's no volume flow because we're keeping the blood, circulating the blood back into the body as we let some of the solutes in it diffuse out. And so if we look at this in terms of all the concentrations, what you get to is an exponential decay solution to this problem. So over time, the the decay rate from the body fluid to the target will occur exponentially, right? Um, so let's take a look. So here we are. C naught, that's where you start. That's where you are at T0. C prime is your target concentration. Um, and so your concentration in the blood goes as this exponential term plus your target that you're headed towards. So this exponential decay towards your target is important. If you look at the tau as your volume over the area of the membrane times your drift, your diffusion constants. So we look at typical numbers, the yield we get is tau, right? What we get out of this is tau is about 1.1 hours. So after 1.1 hours, your concentration, your difference between your concentration you're at and the one you're targeting will drop by 64%, right? So it takes hours, several hours to do this. And you don't want to drop it any faster than that because we already talked about how you already have to worry about getting a headache as you drop the concentration in the blood because it takes longer for the concentration in the cerebral tissue to change. All right, so this is a slow process you're going through. You're just bringing the blood out and letting it exchange, letting the solutes flow through this membrane into the dialysis fluid, and basically, um, uh, you're not you're not filtering, in that the blood isn't going through the membrane. You're simply letting that exchange take place, and you're reducing the concentration of solutes in the blood. Um, Now let's look at different ways we could flow fluids across a membrane. And this is a different topic, but it's related. Um, Countercurrent transport is an important process in biological systems. And let's first look at what happens when they don't flow in the same direction. So we've got a membrane here in the middle, right? So there's this little membrane right there. And we got fluid on top flowing that direction, and fluid on bottom can flow either direction. But the first point we look at, the fluid on the bottom is flowing in the same direction. When that happens, if you've got some solute in the fluid on top and it's flowing to the one on bottom, you start off with, okay, here's what I have on top. And I've got a big difference between the two. And I start decaying towards the other, but this also starts rising, right? Because as you flow from here to there, the concentration goes up here. And so they are asymptotically converging at this midpoint, right? They're asymptotically converging there. Okay, so that's one way. I mean, your fluids are flowing in the same direction across a membrane, and you're hoping to get solutes to go from one fluid to the other. And that's this set of equations up here. And they look really complicated, but looks really complicated because It could be that C in is up here and C out is down here, or it could be that C out is up here and C in is down there, and it's all built into the equations. And you know, it's not really that complicated. Um, the other way to do this that happens in a lot of biological systems is you've got your membrane here, and on top, on one side of the membrane, you're flowing that way, but then on the other side of the membrane, you're flowing this way. Now, what happens when you're doing this? When you're doing it this way, imagine you're going in, right? Well, as your fluid comes in that you're trying to get solutes to flow from, the outgoing fluid already has a good bit of, it's already picked up a certain concentration, right, of the solute. And basically you end up with this constant difference along the exchange membrane, right? So this this gives you a much smoother transition, right? It's linear as opposed to this exponential decay, right? You get this nice linear transition. Um, this countercurrent flows in, um, found in the renal tubules and the villi and the small intestine. We also use it in our own extremities. So if you've got your, if you think of your finger, um, when it's cold, this is important, you are hot, right? Arterial blood is flowing out, venous blood is flowing back. They are exchanging heat along the way. So what's happening is the blood gets out here and gets cold. As it goes back, heat flows from arterial blood back into the venous blood at this point as you go along. And the result is you lose less heat out here. You're conserving heat in your extremities, all right? So because you're warming up the venous blood as it comes back in, because you're doing that, you're not losing as much heat out here because you've already done some of the work getting the venous blood back up. Does it mean you're a little colder out here? Yeah, you're a little colder out here, but you're conserving heat. Um, all right, and that's it for this segment on dialysis and countercurrent transport. It's very important for a lot of different number of subsystems and in general just kind of staying warm.